welcome to this acoustic webinar on the topic of simulation and optimization of acoustic treatment. So quickly, let's take a look at today's agenda. First, we will review several different types of acoustic treatment and the modeling techniques of them in action. So these types of acoustic treatment are mainly the what we call the passive acoustic treatment, including the absorption mechanism, insulation, which, if you remember, is the topic of our last webinar 1 month ago. And on top of that, we have the acoustic treatment by structure damping and acoustic resonance. Then we will review several applications on the topic of acoustic treatment. First, we will look at the wall partition problem by comparing the transmission loss of the wall partition with and without a porous material in between of the two walls. And then two examples in automotive industry. One is on the component point of view, and the other one is on the full vehicle point of view. Then there will be a application on muffler modeling. This webinar will include a demo case, which is a forced response problem of a coupled plate and cavity system, with both the damping treatment on the structure and the porous material treatment in the cavity. Then we will continue on the Q&A session. So quickly, let's review different types of acoustic treatment and typical component or, let's say, devices or materials that are used for the acoustic treatment. Now, for absorption, we have typically porous material like foam, rock wool, glass wool, etc. We also have the acoustic surface coating that is provided by some special material, like some special types of painting on the wall surface, which could provide the absorption capability on acoustics. Then we have insulation, including walls, windows. In automotive industry, for example, we have the engine thermal shield, which also provides the acoustic shielding capability. The car firewall also is a acoustic insulator. And for structure damping, we have typically the silent block design, mainly used in the machinery industry, and the polymer material, which has a frequency-dependent damping characteristics. And all these three types of the previous three types of treatment are mainly used for the broadband treatment for acoustics as well as for dynamics. While the last one type, resonance, through the resonance mechanism, is mainly for the specific treatment on specific frequencies. So typical devices are the mufflers and the acoustic liner on the in the aircraft industry, acoustic liner on the in the nacelle design. So we'll look at this example in a slide later on. So so these are the typical treatments that are used in product design. Now let's take a look one by one on how to model these types, different types, through software capabilities in action. So now for modeling absorption, there are several alternatives in action. So the most basic way could be modeling the equivalent fluid material, so basically air in the example in the automotive cavity. And by introducing the imaginary part of the speed of the sound, we can model a equivalent internal loss of acoustic propagation due to the viscosity in the air. So as we can see here in the property window of fluid material, we have this speed of sound, and we have its real part and imaginary part. So this imaginary part will represent an equivalent acoustic damping by the, for example, trim component in the car cabin. Now, in terms of mathematical equations, we can represent the acoustic propagation, this is pressure, by a real part and the imaginary part. Okay, so now we have this complex wave number, which has this relation with the speed of sound, and by writing the speed of sound in this shape, including the real part and in the imaginary part, we reintroduce that internal loss through this imaginary part. Okay, so this should be the most basic way to introduce a damping in the cavity. Okay, now sometimes when we model the surface absorption, we can use this equivalent admittance or the equivalent impedance method. With this method, which is here, we apply on the surface a admittance. In Actran, we apply an admittance value, which is the inverse of the impedance that could be measured in a quint tube, for example. So basically, we get the impedance or admittance and then enter it here in Actran as a value to this admittance component. Now, in Actran, many values can be frequency dependent. So typically here, both this internal loss by the imaginary part of the fluid, speed of sound, and this admittance condition can be frequency dependent. Okay, now the next method to model absorption is through the modeling of the volume porous material. So porous material are widely used in many types of products. For example, in this automotive industry, we have the foams, rock wool, fiber materials that are used pretty everywhere in the automotive body to assure a good NVH behavior, noise and vibration behavior of the car. So in Actran, to model the porous material, we are based on the BIOT theory. So the BIOT theory is a statement that divides the global properties of the porous material into several categories of properties. So we have the skeleton properties in the porous material, in which we need to model the Young modulus, the density, and the Poisson ratio of the skeleton. And then we have the fluid properties, for example, like the fluid density, but also the fluid bulk modulus, but that are the properties of air, so we have no difficulty to get these properties and enter them into Actran. And then through measurement, we can get several properties that are related to the skeleton and fluid interaction. For example, we have this tortuosity, which describes the global complexity of the micro channels in the porous material, the flow resistivity of the porous material, and this porosity, which is a percentage of the porous volume occupied by the fluid phase. Now, when all these properties are available, then we can, in Actran, use this porous elastic formulation, or in other words, the porous UP formulation. Now, UP stands for U stands for displacement of the skeleton, and P stands for pressure of the fluid cavity. So UP models both the skeleton phase and the pressure phase by using the complete set of biot properties. Now, when some properties are missing, we can still use a simplified formulations. Now, bear in mind, these simplified formulations have their often have their range of validity. Now, for example, the rigid porous, it assumes that the skeleton is infinitely rigid, so we don't model the skeleton phase. And the lumped porous assumes that the skeleton is soft and has a mass effect, however. While the Delaney-Basley formulation and Mickey formulations are two semi-empirical formulations, and they are quite convenient in the sense that we just need to set very few parameters in order to model the porous material. However, as I said, all these simplified formulations have their range of have their validity range. Okay, so that was the three methods that I summarized to model absorption, including the internal loss of the fluid by its imaginary part of the speed of sound, the surface absorption by the admittance, and the porous material modeling using the biot model. Now, to model insulation, in Actran we have solid and shell elements. So by building the solid component or shell component using the finite element mesh, we can model the insulation effect, which is the obstacle effect of any solid object on the propagation of acoustic waves. Now, let's take a look at this example in where we have a gearbox that is radiating acoustic waves, and by putting a cover beside this gearbox, we obtain a modified acoustic directivity at this frequency, a certain frequency around this cover. So in this example, both the acoustic field, which is not visualized here, but the acoustic field is modeled in Actran surrounding these gearbox. So both this acoustic field and this solid component is modeled using finite element in Actran. So this shows the modeling of insulation in Actran. And next category of treatment that I summarized is the modeling of the structure damping. So, Actran is not only a acoustic software; it's also it has also quite rich structure modeling capabilities. So we have seen that there are solid shell elements, but there are also other types of elements like the beam element and beam material, stringer material, and spring material. Also, for the solid material, there are isotropic material, transverse isotropic material, and orthotropic material. Okay, and so all of these solid materials, they support the complex Young modulus in their properties. Now, for example, for the isotropic solid material, here I set up an example of PVB material, which is a polymer material, and we can see that in the Young modulus here, there is a real part and an imaginary part. So similarly to the modeling of the speed of sound in fluid material, here the imaginary part of the Young modulus also represent a damping behavior. Okay, so we have seen the mechanisms of absorption, the mechanism of insulation, and the mechanism of damping. In product design, especially here, I'm showing again an automotive example. In the automotive industry, many times these three mechanisms are combined together using a multi-layer structure design. So here in this figure that shows a typical Ritter automotive, today it's called automotive example. We see a four-layer design. So from below, we have the thin metal layer, and then this layer is connected to the damping layer, which is a type of polymer. And then we have the porous layer that goes above this damping layer, and then the complete multi-layer structure finished with this heavy layer. Okay, so to model these types of component in Actran, we just use the solid shell component and mesh each layer with their corresponding thickness and their corresponding material properties, including the real part and imaginary part of the Young modulus, including the biot properties for porous material, for example, and all these properties can be frequency dependent. It's interesting to see that actually for these types of for this type of multi-layer, we typically have a frequency that is called a cut-off frequency. So above this frequency, the dynamic loading or the vibration from the incident part is reduced through the complex structure to the transmitted part. However, below this cut-off frequency, we typically have this amplification effect. Now, the reason behind that is that these complex layer structures is dynamically similar to a damper mass spring system. So typically in dynamics, we are familiar with this phenomena that below a certain frequency, the dynamic behavior is amplified until getting that frequency. Now above that frequency, the dynamic response is reduced. So using Actran, we can design such type of multi-layer structure by changing the properties of each layer, by changing their thickness, and then to achieve a cut-off frequency and optimum reduction according to the frequency. Okay, now the last phenomena that we mentioned is the resonance mechanism. So resonance mechanisms are usually employed in muffler design. So to model an acoustic muffler in Actran, we simply build this a volume mesh that represents the shape of the muffler. So this is a quite typical expansion chamber, which is the most basic muffler design. And in the case study later on, we will see that there are more complex mufflers integrating the perforated sheet and the porous material in the muffler. Now, with this simple muffler, in Actran, we just built a volume mesh here. So with this volume mesh, we can simulate not only the 1D transmission phenomena, but also the complex acoustic wave transmission through this muffler. So we're not using a 1D assumption in the muffler study. And in terms of modeling, we will apply a incident acoustic wave at the inlet of this muffler. So part of the wave is transmitted to from the outlet, and some of the wave is reflected due to the shape change back to the upstream. And the indicator in the muffler performance is often a transmission loss, which is the ratio of the incident power and the transmitted power that are calculated automatically in the Actran computation. So now the next type of resonator is the Helmholtz resonator that are used in many types of products. Typically in the acoustic liner of the aircraft engine, as we can see here, in this, under the surface of the nacelle here, we have this Helmholtz resonator buried below this surface. And typically in Actran, we will most of the time not model the shape of that honeycomb structure. Instead, there are facilities that allow measuring the surface impedance of the liner, and in a acoustic finite element model. So this one is axisymmetric acoustic propagation model representing this nacelle. We will plug in the impedance value of that liner on this surface to account for the absorption by the liner. So these are some reviews of different mechanisms of acoustic treatment. Now we will review several industrial applications. So first one is a validation of the modeling of multi-layer structure in Actran. And this validation is realized by experiment. So in this test setup, we have our test pieces is a sandwich layer, okay, including two plates sandwiching a porous material. Okay, and this multi-layer structure is excited by this shaker, and its get vibrates and radiates acoustics into this anechoic room. And in the Actran model, you can see here we model through finite element different layers of structure and porous material, and the air volume that is beyond the surface of the heavy layer. And two types of material are compared. One is the foam type porous material. The other is the fibrous type of porous material. So we were looking at different indicators each time comparing simulation and measurement. So first, some dynamic indicators. The acceleration at the center of the panel with the fibrous trim included. and then the mean velocity of the upper layer, of the heavy layer, with the fibrous trim included. And then the sound pressure level, so that is measured at the microphone that's 1 meter above the plate, and there are two types of porous material compared, fibrous trim and foam trim. As we can see that we obtained very good agreement between the Actran simulation and the measurement. Okay, the next example is the demo case that I used for the last webinar on a wall partition example. So just to remind you this problem, we have a wall partition, including on each side a plaster layer, and then a very thin air gap, and then in between thick rock wool layer for the damping effect. So we were, through Actran modeling, we were able to obtain this red curve, okay, which is the transmission loss through the sound transmission loss through this complex layer. Now, if we simply replace the rock wool by air property, so we are removing actually the rock wool material, then we get this blue curve. So there are two observations. First, we see quite a shaky curve, so that are created by the cavity modes of the air replacing rock wool, and then we see a reduced transmission loss, which means increased transmission through this wall partition. Okay, so now the next sample is on the complete automotive vehicle level. So we had seen just now a validation problem on a component level. Now this time is on the system level. So in automotive industries, there are many trim components, many of them acting as dampers, insulators, absorbers, but some of them will behave as a combination of, for example, insulator and absorber. So we have the floors, the headliners, the door trim, the dashboard, the seat, the wheel well, and the trunk floor, etc. And many of these trim components, they are the multi-layer components, as what we have seen in the previous example. Okay, so this example is on the airborne acoustic transmission from a simplified tire noise excitation to the interior of the car cabin. Now, to model this transmission behavior, we divided the task into two sub-steps. So in the first step, we used simplified acoustic sources. So they are basically monopoles around next to the wheel, and the radiation and scattering of this source will result in a surface pressure on the car surface. Okay, and in the second step, we will excite the complete vibroacoustic system of this vehicle, including the trim component, by this surface pressure. So as we can see here, a image on the exterior mesh for the first step, the exterior air volume used for the first step. And here, this image shows the four trim components that we considered in this example. They are the dashboard, the floor, the tunnel pad, and the headliner. And when we zoom on each of these components, we see a detailed finite element modeling of this, all of these 4 trim components. We can see that different layers with different thickness representing different material composing this, all these components. And to evaluate the effectiveness of the acoustic treatment, here we are looking at a noise reduction indicator, which is very relevant to airborne excitation. So this noise reduction indicator is a ratio between the mean square pressure that is applied on the exterior surface and the resultant mean square pressure that is in the car cabin cavity. Okay, so we can see here the treatment has quite limited effect below 300 Hertz, but starting from 300 Hertz, we have a increased noise reduction, as we can see here, when all the trims are taken into account. We have this difference of 13 dB here at this frequency of 375 Hertz, and here this is animation of the pressure field inside the cavity at this frequency without and with the acoustic treatment. So often it is believed that the porous material is only effective at a very high frequency, for example, starting from several thousand of Hertz. And this example shows that actually at this relatively, let's say, lower frequency range, 300 to 400, already have this effectiveness of the porous material, which is physically not strictly due to absorption of the acoustic waves by the porous material, but due to the compression of the porous material by the neighboring plates on each side. We have this dynamic reduction, and in turn the acoustic reduction in the cavity. So this is a very speaking demo that shows the effectiveness of the acoustic treatment. Okay, so the next example is a muffler modeling. So we have seen the modeling of the simple muffler, and here we will model a complex muffler including perforated plate design and the porous material usage. So this example is a cylinder muffler, okay, which is different from a simple expansion chamber in the sense that the central duct and this expansion volume is separated by this perforation plate. So the perforated plate is a sheet that has that is punched with many holes on it. And to model the acoustic, to model this system, typically we in Actran we will not mesh this perforated plate using finite element method, which could be done, but that could be quite tedious. Instead, we use a acoustic transfer admittance method, using this relationship between the acoustic velocity and pressure across this perforation. We could model the equivalent behavior of the perforation, so equivalent behavior including the viscous damping through this perforation. And these terms in this transfer admittance matrix can be calculated based on the several characteristics of the perforation plate. For example, if we have the distance between the hole, the thickness of the plate, and the fluid characteristics, we could calculate this admittance matrix. So there's a utility in Actran also to calculate this admittance matrix, which is really handy for simulation work. Okay, now a validation on the Muffler case. Here we have, so on top of the previous expansion chamber with perforation, we are adding here a porous material on the expansion chamber. Okay, and we calculate the sound transmission loss through this muffler and compare with the measurement, and we see that very good correlation were obtained between test and simulation. And typically at lower frequencies, we see this periodical behavior. This means that we are in the plane wave region. So the acoustic wave propagation is through the form of plane wave. And as frequency goes on, we have this complex pattern, and which means we are going beyond the frequency range for plane wave propagation. We have starting to have complex waves propagating in the system, and this phenomena can only be modeled using a 3D acoustic software like Actran. Okay, so those are the application reviews, and I will finish today's presentation by a small demo. Okay, so it's quite a simplified model just to illustrate the idea of introducing damping in a system. We have this coupled plate and cavity problem. So basically we have a cavity here, and on top of that we have a flat plate that is coupled to the cavity, and then we apply a point load on a certain point of this plate, and then calculate the acoustic response at this point in the cavity. So the original problem has little damping. There was some damping on the plate, but not much damping, and there's no damping in the cavity. And we developed this model into two ways of acoustic treatment. So in the first way, we are adding a foam in the cavity. Okay, so we see at the four corners of the cavity, we're adding 4 pieces of foams, and on the other way, we increase the structure damping through the imaginary part of the Young modulus on the plate. So we initially we have this Young modulus, which is so this number we have the 7 to the 10 times 10 to the power of 8 at the imaginary part, and now we are changing this 8 to 9. So we amplify the damping by a factor of 10 here. And okay, I will switch to the Actran interface and show you how this the model is done in Actran. Okay, so now we are looking at the graphical user interface of Actran. where we build all the we bring the mesh in and build the Actran analysis. So this is a direct frequency response analysis. So we work in the in this case we work in the frequency domain using physical coordinates. And so here we have this shell component for the plate, and we can see that it has these material properties, which is that those of a aluminum material. Okay, and in the this plate is connected to the cavity. Okay. And in the first way of changing the model, we are adding a 4 foams here. I'll use another color. So these 4 foams are at the 4 corners of the cavity. Okay. So here we use a simplified formulation for porous modeling. We assume that the skeleton is rigid, so we use this porous rigid formulation, and this results in a This resulted in a limited number of properties that are required. And this point load is applied here on the top of the plate. I will change this plate into another color here. Okay. Yeah. So to change this model into a higher damping problem in the plate, it is by changing this Young modulus here of the plate. Basically, we change here the imaginary part of the Young modulus from 8 to 9, and in this way we are adding the damping in the structure. Okay, so that is a view of the graphical user interface. The results, I will not launch the computation now. It has been launched previously, and we obtained different results for the 3 different models. On the basic model with little damping on the plate, but no damping in the cavity, we see this this curve for the sound pressure level on that microphone point. Okay, we could obtain a good correlation between the Actran simulation and analytical solution. So for this simple problem, we have the analytical solution by model method, and we could identify that different peaks are correspond to different eigenfrequencies of either the plate or the cavity. So by calculating the mode of the plate and cavity, we could say that the peak at 64 Hertz is due to the plate mode, 100 Hertz due to the plate mode, etc. And at 228 Hertz, it is due to the cavity mode. Now it is interesting to see that here we add, so we change the damping in the plate from lower damping to a higher damping, and by doing this, we could see that those peaks that were previously related to the plate modes got reduced, and the peaks related to the cavity modes stay almost unchanged. So this is the influence of the added damping on the plate. And then when we add the foam component here on the same microphone, we see that the peaks that were related to the cavity mode are reduced. Okay, this one and this one, while the those related to the plate mode got almost unchanged. So from this simple example, we could see that the effectiveness of the acoustic treatment on the plate and on the cavity with regarding to the cause of that different peaks. So that was my presentation, and it ends today's presentation session. And so thank you for attending this acoustic webinar. And let's start the Q&A session. Univers, please.